so. And my talk is sort of between le marteau et l'enclume, as one says in French. So it will be between the talk of Carlo, who told you everything about single particle localization, and the talk of Dima, and the later talks, both experimental and theoretical, Denise and Emmanuel in particular, that you will hear during this week, we will more concentrate on something which you know as many-body localization. And I will try to set the stage and the vocabulary that maybe will clarify a certain number of points on what are these various beasts. I'm not running a marathon. By the way, I wanted to thank officially the director of the school for having put back the canistrelle in baskets for the break, the little break, because this was really missing during the COVID years. Yeah, that's thanks. As a Corsican, I appreciate deeply the thing. Okay, so more seriously, let's go back to the thing. I'm not running a marathon, so don't hesitate to interrupt me. I will cover things for which I will not be able to give many technical details. So if you're an experimentalist, or worse, if you're a mathematician, it could be difficult to follow. And so don't hesitate to shout, stop me, and tell me I don't understand. Can you explain? We have the board here. We can do whatever we have to do. If you want to know more on the activities of the group, you have here the link, and I cannot resist showing you the group. Of course, in this course, I will cover activities which have been done by many other people. You see that Giacomo is here, hiding in the middle of the room behind the mask, so don't hesitate to turn to him if you have questions on some of the things that I will not tell you. Okay, more seriously, what I will tell you concerning my own activity has been done in collaboration with many people, too many to mention them, both on the theory side, on the experimental side, both on the cold atom side and on the condensed matter side. So I wanted to at least have a slide with their names here. Okay, so let's go back to Anderson localization. You heard earlier this morning that we have this incredible paper of 1958 due to Anderson, where he showed that even with weak disorder, you could get a complete change compared to the plane wave states of a free electron, and that can lead, if you solve the Schrödinger equation, to localized solution for free, essentially free, meaning independent particle, non-interacting particles. And I want to point out, of course, that if you have non-interacting systems, then the energy of each particle is conserved. The disorder scatters, of course, the particle, changes their momenta, but does not change their energies. So you solve this equation, I would say energy by energy, and that's what makes the problem, if not simple, at least not totally untractable. And this is, of course, a field which is still very active, despite being essentially, let's say, 70 years old or 60 years old now. In the cold atoms, I cannot resist showing you these experiments with the man of the year who is here, Alain Aspect, because this was a big success, I think, of cold atomic gases to be able to provide a direct observation of the Anderson localization of matter waves in non-interacting systems, either using speckle disorder in the group of Alain Aspect at the Institut d'Optique, or using quasi-periodic potentials in the group of Massimo Inguscio. I won't discuss this, but I'm sure there will be other talks during the week where we will hear more about this. So I just wanted to mention that cold atoms have been an important component in the field of Anderson localization. Okay, so this is all good and well, but this is for non-interacting particles. Now, if you think about condensed matter, nobody complained this morning when Carlo was talking about, you know, all these nice electrons which are moving in metals and blah, blah, blah. Electrons have Coulomb interaction. They repel. They are not free particles. So how could anything that he said in the morning be true when you have 10 to the 23 particles which are interacting deeply via Coulomb interactions. So we have to worry about Coulomb or other interactions. Interactions are present physically in many of the systems where we can study disorder. I think it's only if you have photons that you can avoid essentially interaction. So, but photons suffer from other problems like loss, essentially. And also, of course, you have the question on what will be the influence of these interactions on localizations. And there you see that this is something which has many sides to this problem, because it will not be the same thing if these interactions are repulsive, and if it's contact interaction, for example, particles only see each other if they are on the same site, or if they are attractive. Attractive interactions, you know, lead to superfluidity or superconductivity, and everybody will tell you a superconductor resists to impurities. So if you have a superconductor and you put a little bit of disorder on it, you shouldn't have to worry about Anderson localization. So the question is, how will this competition or collaboration, I don't know, at that stage, on that slide, between disorder and interaction will take place. We also might have to worry about the fact that the interaction can be long range, in which case, of course, many particles will see each other very far, even if they are localized. So all this physics is absent in the canonical problem or treatment of the non-interacting system. Why we can do this still and have something very relevant for condensed matter, I'll comment briefly later, but I want to point out that worrying about interactions is, of course, a very natural extension of looking at the problem of Anderson localization for non-interacting particles. So, of course, in this lecture, I will try to tell you about disorder and interaction. I don't need to convince you that this is a very difficult problem. If you have interacting particles, forget about disorder. You know that if you have, let's say, n sites, and let's say you can have a particle or not have a particle on one site, then the Hilbert space is growing not linearly as if you have non-interacting particle, but in presence of interaction, you have to worry about the whole Hilbert space because everything will be coupled. So the size in which you have to describe your problem in terms of components of your wave function or whatever is 2 to the n. So putting that on a computer, you know, for non-interacting particle, it's still feasible. You can easily diagonalize matrices which are 1,000 by 1,000. It's just 1 million elements. Now, with memories on typical computer, that's a small perturbation on your memory. But if you have 2 to the n, look at what will be the size you will be able to look at in terms of system size. You're dead after, let's say, 20 sites. Essentially, you die. I mean, your computer, you cannot hope to make any exact solution of this problem. So this is clearly a step beyond in complexity, just is to solve simply correlated problems even without disorder because of the sort of nature of the Hilbert space and the wave function. So we have to face this problem. As I was mentioning, it has many aspects. The nature of the interaction, whether it's long range or short range, whether it's repulsive and attractive. And I will try to describe somehow moving through the centuries, a little bit like Carlo did, going back to Neanderthal and moving forward, what people did to try to tackle this kind of issues. So this is something that was actively studied in the 80s, actually, mostly for fermions. Because again, fermions are condensed matter. You get electrons, and it's very natural to say, oh, well, in condensed matter, we have this interaction that we have to worry about. The reason why people didn't worry about is because there was a guy named Landau, Lev Landau, who invented a fantastic theory, which is called Fermi-liquid theory, which says that if you have fermions, and in some circumstances, you can essentially completely forget about interactions with the price of renormalizing some parameters of your fermion. So instead of putting the bare mass of the fermion, you put a renormalized mass by interactions. But once you have done that, Landau tells you, well, you can essentially forget about the interactions. So that's why to describe condensed matter system, it's very successful to think in terms of non-interacting particles. That's not really original particles, that's so-called Landau quasi-particles, but that's a good starting point. Now, of course, if you have disorder, you can question whether the very existence of this theory by Landau, the Fermi liquid theory, will survive the disorder. After all, if you slow down the electrons, because they become diffusive because of the disorder, well, they will spend more time near each other, so you can expect naively to reinforce considerably the effect of interaction. So maybe Landau Fermi liquid theory will not be valid anymore. And there were a lot of papers in the 80s that studied this either using a straightforward perturbation theory, Feynman diagram, beautiful papers by Ed Schuller, Aronoff, and Lee. Then a more powerful technique, which was put forward by Sascha Finkelstein using the concept of renormalization group to study two-dimensional fermions. And with Heinz Schulz, practically during this period, we looked at fermions in one dimension using techniques that I won't discuss here, which are called bosonization and also renormalization group. And I will just give you one result of this time, I would say, but I think it's worth having this a little bit in mind because it shows you the complexity of the problem and really where we are in our understanding in high dimension. High means d equal 3 essentially, or d equal 2. So you will find more details in this Varena lectures where I discuss this thing in more detail. So let's look at a phase diagram where we have here the disorder, and here I put U, which is a kind of parameter for the interaction. Think of it as a local interaction if you want, but actually no, I want to describe real solids, so U is actually a coefficient in the Coulomb interaction. If you want, it's the charge of the electrons or something like this in my problem. So there are axes we kind of know. If we are on the non-interacting axis, well, we know that in 3D we have a mobility edge which separates a metal from the localized phase that you heard in Carlo's talk, and there is a certain threshold of disorder above which everything will be insulating, everything will be localized by the disorder. That's Anderson localization. That's the axis that we know and love for non-interacting particles. On the other hand, if we have no disorder, so I put Anderson here. On the other hand, if we have no disorder and we move by increasing the interaction, at least for moderate interactions and even pretty strong interactions, we have Landau Fermi liquid theory. This theory where I told you, you can just renormalize one parameter, like the mass of the particles, and then you can think of it as free particles. Okay, that's on the zero disorder axis. What happens beyond, we'll come back to it. Now, people, of course, naturally build on these two aspects, and doing perturbation theory in the disorder, they came to a theory known as weak localization, where you start doing perturbation on the top of the, let's say, non-interfering disorder, and I'm sure you will hear much more about this in the talk of Bart van Tigelen later this week. This is essentially a perturbative theory, but if the disorder is weak, then essentially you can extract a lot of very relevant experimental results here. If you want to go beyond, you have to consider the feedback of the disorder on the interactions, the feedback of the interactions on disorder, and then we get Altshuler, Aronoff, and Lee, and we get Finkelstein's RG. So essentially this little corner here, we have reasonable tools to be able to describe the combined effect of interactions and disorder, as long as the temperature is not too low, as long as the disorder is not too strong, as long as the interactions can be treated, are weak enough, let's say this technology reasonably works. And then the rest is terra incognita with some limits that we control. If we go non-disordered to very, very repulsive, so very low density actually, then the long-range nature of the Coulomb interaction makes it that your electrons will crystallize. And they will form what is known as a Wigner crystal, which is a phase of matter that was predicted by Wigner, whatever, 1930 or something like this. And for that, you need long-range interaction. If you have short-range interaction only, you will not get this Wigner crystal. And then, of course, this Wigner crystal will pin on the disorder, will be distorted, and so you get a very interesting theory that is a pin solid of electrons, not anymore a liquid of electron, Fermi liquid or free electrons, but a pin solid of electrons here. And this is something that people have studied in semiconductors, the same one in which there are the fractional quantum Hall effect, for example, and more recently in something called TMDs, transition metal dechalcogenides. This is a very exciting phase of matter because let's say it has the unusual properties of creating a crystal of electrons and then disordering it with a disorder. And then, of course, the very natural thing, but that's sort of urban legend, there is no calculations for this, is, by the way, this has glassy physics. This is in the universality class of what we call glasses. And then is to say, okay, we have a solid here, here we have a liquid, so there must be some kind of melting line between the solid and the liquid. And what is the way the melting takes place, whether we have an intermediate phase, we don't know. There were even proposals at the time that there could be an intermediate phase which was delocalized in between this regime and this regime. Well, okay, I don't want to go into this debate, just to show you this, to show that this is really a difficult problem and people have not really found yet good tools to attack this intermediate region. So the little corner here is okay. The very crystallized solid pinned by the disorder is okay. And then in between, it's really terra incognita. And then your attitude you can think about your attitude to that, as Carlo was mentioning. Either you say, well, people try for 20 years to solve this, let me go and do something else, or you say, maybe that's something I want to have a look at and try to have a shot. It's certainly an extremely difficult problem. Okay. I just want to point out that that's all what I would say about fermions, essentially. I will move to mostly bosons because it's simpler and it's more easy to explain like this in a very short lecture. I just want to point out for bosons, the situation is even worse. Because if you have bosons, free bosons is a pathological system. Imagine you have disorder which is binary, which is plus something and minus something. You can always find with a certain probability a region of space where your disorder will be minus something over L site. It's exponentially rare, but you will find it. It's a rare event. Okay. So in this region, the particle will be trapped, so the momentum has to be 1 over the size of the system by sort of uncertainty principle. So you lose kinetic energy by not delocalizing the particle over the whole system. You lose an energy which is 1 over L square, P square over 2m. You lose an energy which is of order 1 over L square, where L is the size of this region. But you gain an energy V0, which is coming from the disorder. So if you find a region which is large enough, you will, at some point, always find a favorable region. So it's rare. It's a rare event, but if you have an infinite system, you will always find a region where you can put 1 boson. But if you have non-interacting boson, if you can put 1 boson, you can put 10 billion bosons in exactly the same region. And now you see what you've done. You've put all your bosons in a finite region of space. So the density is infinite. As soon as you will turn on interaction, this will explode completely. And the boson will get out of this finite region of space and start occupying really the thermodynamic system, the big L system. So anything that you can get out of free bosons, fermions don't suffer the same fate because of Pauli principle. This saves you. But if you have bosons, you're forced to put interaction from the start. Otherwise, you get a solution which is simply nonsense for describing the effect of disorder. So if I put interaction, this finite region will explode into places where particles can sort of get localized individually, and repulsion then will not play a role. So this is a very interesting problem. Yep. This pathology, that the way I describe it here, is only at 0 temperature, but actually the fact that you would get these rare events would survive even at finite temperature. It's just that if you find one state which has a negative energy, you can put as many particles as you want in the same state. You can get a condensation of bosons in this state. So, okay, this is 0 temperature, but I'm sure you get bad things which would still arrive at finite temperature without interactions. Yeah, by the way, again, don't hesitate. I say the same thing then, Carlo, don't hesitate to ask questions. So they are needed from the start, and this is something I will discuss much more in the course of this lecture. Now, let me just mention that, of course, we talk about disordered system, but one quantity that is of interest, I know in cold atoms we look at wave functions and things like this, but if you're a condensed matter experimentalist, you won't see the wave function, so the only thing you'll measure is the conductivity. And at the end, that's what tells you if you're localized or not localized, if you have an insulator or if you have a metal. So, one question that people ask very early is, what is the transport at finite temperature? If you are at 0 temperature, you're Anderson localized, your conductivity is 0. You get an insulator. If you have a metal, the conductivity is either finite or infinite if you have a superconductor. But at finite temperature, naively, you would expect that whatever happens, you get a finite conductivity. As we will see, it's not as simple. And the person who sort of first guessed what was going on is Sir Neville Mott, who is here. And he invented a concept which is very beautiful, which is called a variable range hopping. So let me try to describe it to you. Imagine that you get localized states, which are, okay, this one has this energy and is here spatially, this one has this energy and is here spatially, this one has this energy, and so on. And now you put an electric field which tries to move the particles that way. How will it happen? You can say a particle which is in this state can try to jump, okay, I did it the opposite way on the graph, but okay, can try to jump from this state, which is occupied, to this state, which is empty. And then the next particle will jump, and the next particle will jump under the influence of the electric field, and little by little you will get a current. And the conductivity will depend on how easily this particle can jump from this side to this side, and so on. You immediately see that this is only possible, by the way, if you get somewhere to dump the energy. Because if I go from there to there, I'm not respecting the conservation of energy, so I need to transmit the energy somewhere. It's not a problem if I have a thermostat, like in the room, we transmit the energy and we receive the energy from the room. And globally, we conserve the energy, but not individually. So if I have a thermostat, if I am in equilibrium with the thermostat, then I can do these jumps, and I can move the particles. If I don't have the thermostat, we'll come back to this. So what is the idea? Mott said, let's assume we have a thermostat, phonons, vibrations of something and whatever, and this thermostat has a certain probability of having an energy which is given by Boltzmann, exponential of minus beta e. For the mathematicians, don't be afraid. This is not only physics, but this is English physics, which means it's really physics with the hands. But the guy got it right, and got it right 70 years before everybody else. So one has to respect that. This is called genius. Mott got the Nobel Prize, of course, for his work. Not this one, but for other works. But you will see, it's a beautiful theory. So you say, okay, I get my thermostat, which has this law of probability. Now, if I want to jump from this place to this place and they are exponentially localized, I have a matrix element which is exponentially small, which is the distance between the two states divided by the localization length, the typical size of the wave function. And the sort of probability that I have to hop, not to hope, but to hop, is given by sort of the product of these two. I need not to involve the thermostat into too big energy exchange, otherwise I'll pay the price, but I also cannot jump too far because otherwise I have a very small overlap of the wave functions. Okay, now, what is my chance of finding a state with a given difference of energy? Well, if I'm jumping at a distance L, I cover a volume L to the D, and then if I know the density of states, the number of states per interval of energy, I will find one state when this volume, L to the D, times the interval of energy times the density of state is of order 1. So I can consider that this quantity is of order 1. And you see it gives me a relation between L and E, and now it's a simple minimization problem to find the optimal distance at which you will hop. If you put this distance larger, you have more chance to find a good state close in energy. But, okay, you have a very small overlap. If you make this distance small, this overlap is much bigger, but you will pay the price with the thermostat. So you minimize, and when you minimize, you find this beautiful result that the conductivity is exponential of the inverse temperature with factors which depend on the localization length, the density of state, exponential of the temperature to a power 1 over d, where d is the dimension of space, plus 1. It's remarkable results, which says that you get linear response, you get something where you will get a finite conductivity at finite temperature, but this response depends in a very peculiar way of the temperature, and is exponentially small. You see, this is inverse temperature, so at small temperature, this number is large, so this conductivity is exponentially small, and it's power which depends fractionally on the temperature. So in 1D, for example, it would be the square root of the inverse temperature, and this is known as Mott variable range hopping. Now, this is in presence of a thermostat. What happens if you have no thermostat? Well, there is a problem we know how to solve. It's the 1D non-interacting problem. All states are localized. And then you find that if there is no thermostat, there is no possibility to do this jump because you cannot conserve the energy. And you find that the conductivity is 0 at any finite temperature. You can warm up your system as much as you want. It stays an insulator at all temperatures, which is a little bit disagreeable in terms of physical intuition, but which is the mathematical solution you will find of the fact that all states are localized. And so you see immediately that we can expect then that there will be sort of differences whether we have a system in contact with a thermostat or not. Except you could say, oh yeah, I don't have a thermostat, but I have interactions. So with interactions, one particle can exchange energy with the other particles, and therefore the rest of the system can serve as a thermostat for one jump. And that's a question. That's an open question, which is when I have no interaction, I know the answer. I cannot do anything in terms of transport. But if I have interactions, can the system be its own thermostat by exchanging energy between the particles? Yes? Well, I'm talking quite generally. If I am here not in 1D, because there exists a mobility edge, you can always go through the states which are non-localized, and then you get a finite contribution to the conductivity. So in 1D, this is the place where you can show that this is 0, 0. If you're in more than 1D, there is a contribution from the part of the spectrum which is delocalized quite logically. But yeah. So if you believe the gang of 4, which was alluded to in the previous talk, in 2D all states are also localized, so at least naively you would also expect the conductivity to remain 0. It's more subtle because it's less violently localized, but you, in principle, for non-interacting system, have no mobility edge in 2D. Other questions on this? Good. Okay. So this will set the stage, and in a way will tell you what is different from this talk and the talk you will hear this afternoon from Dima, who, if he does like me, is preparing his talk right now. Sorry. I know the feeling. So I'll try to use a vocabulary which normally I don't use, but if not, we'll get nuts. So I'll try to tell you the difference between LIP and MBL. So what do I mean by that? There are two cases. One, we look at system in presence of a bath. We put a bath. It's morally there. I have a very weak coupling to phonons, or I have a way to exchange energy, or I'll do something like this, but I ensure that my system will thermalize and will have this exchange of energy. Then I know that I reach equilibrium, whatever happens, all phase space is reached, and for transport, I have a priori this variable range hopping mechanism when the temperature is finite. This is what I will call the localization of interacting particles. It's as many body localization as many body localization. It involves localization and it involves a many body problem, but just to avoid confusion in the terms, I will call it LIP. So this is when there is a bath, when there is, at least in the calculation, one put the system in contact with the bath, or one looks at timescales long enough that you consider that the bath has acted. And then there is the very interesting question that you will hear in several talks during this week, which is what happens if you don't have a bath, if you decide that you really have an isolated system. So in condensed matter, it's a little bit difficult to have a situation like this, but of course cold atoms have provided a very natural path in which you can study these issues because they are naturally excellently isolated systems, and you can really ask this question not only on a theoretical way, but also on an experimental way. So if you have absence of a bath, then the question of whether you can do these jumps, the very question of ergodicity, whether you will be able to explore the whole phase space of your problem is now really open and subject to debate in presence of interactions. Without interactions, we know the answer. We have the exact solution of non-interacting particles, at least in 1D. So you saw conductivity is 0 at any finite temperature, but with interaction, the question is open and has been addressed, and you will hear by this in various talks later during this week. And this is what now is known under the name many-body localization. So I will reserve the name many-body localization to these issues. I won't discuss them very much during my talk because they will be covered extensively in several other talks. But I just wanted to set the vocabulary so that there is no confusion. We are all talking about interacting particle. We are all talking about many-body systems. We're all talking about effect of Anderson localization in these systems. And the difference will be whether we assume contact with the thermostat or we don't. Yeah, Javier.
In the first case, localization of interacting particles, is there some sort of hidden assumption that the states of each particle look like a single particle state?
No, because it's really a many-body problem, and you cannot reduce it to individual particles. It's as much a many-body problem as the other problem. And again, the question is whether you will have the possibility of either exchanging this energy when you try to do transition between the states or not.
The many-body states in the first case is not a perturbed version of the single state particle.
No, not at all. No, it's really a full many-body state. And it's just that here we will implicitly assume, for example, at t equals 0, that you go to the ground state. it just take long time, but you go to the ground state because your thermostat allowed you to reach the ground state. Here, if you start from a state which is not the ground state, maybe you will never reach the ground state because you're isolated. So, and actually, I'm sure Emmanuel will talk more about this in his talk. Okay. So that's the main difference. Both are many-body localized situations. And again, it's a question of ergodicity and the possibility for the system to exchange energy with the outside in infinitesimal quantities. We are not talking about an out-of-equilibrium system where you put it in contact with a big bath, which makes a lot of change to the system. We're talking about, like in a statistical physics course, the thermostat is there morally, but you never see it in the calculation. So in this course, in the next 39 minutes and 36 seconds, I will tell you about the localization of interacting particles. And again, Dima this afternoon will chain in with the many-body localization. So I assume existence of a thermostat. I will look in 1D, both because I love 1D, doesn't show, but I'm a 1D guy, trust me. But also because it has the maximum effect of interactions. If you're in 2D, you can have infinite repulsion between these particles. They can cross without any problem. You move in 2D because you walk on the ground. You have infinite repulsion between yourself. You can avoid each other without problem. In 1D, think about cars in a lane. You immediately transform individual motion into a collective motion. When you will queue for the lunch, I'm the only one standing between you and lunch. So when you will queue for the lunch, you push the person in front of you, who pushes the person in front, who pushes the person in front. Immediately, an individual motion is transformed into a collective motion. So the effect of interactions are maximum in 1D. And in the same way, the effect of disorder is also maximum in 1D. This is where all states are localized for non-interacting particles. So that's a nice place to look for the competition between disorder and interaction. I will not say anything. If you want to have more details, I can recommend to you a very good book on one dimension. I will not say anything about I will only talk about 1D bosons plus interaction because of the limited time. If you want to know about fermions and quasi-1D, I recommend the poster of Giacomo. You will know more about these exotic situations. Of course, I'll be very happy to discuss them as well. But here I will concentrate on 1D bosons plus interactions. I've put here general references that you can find. It's not worth spending time on this. So let me discuss what happens if I take 1D interacting bosons. So the Hamiltonian is very simple. It's the kinetic energy of the bosons here. This is an interaction term, which actually is a delta function. The bosons, two bosons see each other if they are exactly on the same site. You can put more complicated interaction potential. It doesn't change in any essential way what I'm going to tell, as long as it's short range. If it's long range, it's a different story. And then you put a disorder term, which is a random chemical potential, which varies, let's say, from site to site. You can do variations on this theme, but I'll concentrate on this. So I have a random value of the chemical potential on each site. I have a delta function potential. This part has a name. It's called the Lieb-Lininger model because it was solved by Elliott Lieb in the 60s, essentially using Bethe-Ansatz. Solve meaning he showed that it was solvable. No, I joke. But he provided very, very important solution. But there are now new other technologies, some of which developed by Duncan Haldane to tackle this 1D system. So without disorder, we know everything that there is to know about this 1D bosonic system, even with interactions. We control very well the 1D interacting system of bosons. In presence of disorder, that's a tough cookie. So I'll come to this. We solved it together with the late Hein Schulz, using, again, techniques that I cannot describe, but I'll be happy to tell you more if you want to. It's known as bosonization. And we could obtain a pretty good idea of what is going on in this system. And in particular, we could show that there is a many-body. Again, I insist, this is a many-body phase. There is a many-body localized phase, which now is called the Bose-Glass, which is, we can discuss the terminology, but which represents 1D interacting bosons localized by the disorder. I just want to point out that in 1D you have to be a little bit careful when you discuss disorder, contrarily to 2D, because there are essentially various components of the disorder. If you are in 2D, you can scatter particle on impurities in a continuous way. But in 1D, you have essentially two possibilities. Either you go straight or you backward. And so you can sort of Fourier separate your disorder into two components, which are largely independent. The forward scattering, which is Fourier component with Q close to 0, and Fourier component close with Q close to 2kF for the fermions, and 2 pi rho 0 for the bosons. And these two disorders act a little bit separately, if you want. The Q equals 0 is like a very slowly varying chemical potential. When I say slowly, I mean it varies with a length scale much larger than the typical interparticle distance. This provokes distortion of the density, but doesn't have any serious detrimental effect in 1D. It's not true when you will look at quasi-1D systems, but in 1D it doesn't do much. So the forward scattering, as people call it, doesn't lead to localization. It's sort of an innocent perturbation. It can do things if you have other phases. But the backward scattering, so the component of the disorder which have essentially the same periodicity than the typical interparticle distance, have a very dramatic effect. Imagine that you had a simple sinusoidal that would be exactly at this periodicity. Then you immediately see that your disorder will pin on this modulation of the potential. You would get one boson in every minimum. Of course, this is not a regular sinusoid, otherwise it would not be disordered, but the effect is a little bit the same. You have this distorted sinusoid, and then you try to put one boson in each one of the minima, and you have to compromise between the repulsion between the bosons and the happiness of putting one boson in each one of the minima. And this compromising situation, if I can say it that way, is what leads to localization. You can study it using renormalization group equations. I don't want to go in detail. And what you will find is what I will show you in the next slide, is that you have two possibilities. Either at large length scale, the disorder disappears, and then you get a superfluid, interacting bosons like if there was no disorder. And or the disorder grows under renormalization, dominates everything, and then you get the Bose-Glass, you get the localized phase of system. So the phase diagram looks like this. Here is the disorder strength, mostly the backward scattering, but of course you can take a disorder and you have both components. This is the repulsion. Now I'm talking about contact repulsion. And essentially you have a phase diagram which is no repulsion, pathological localization of the bosons, as we were discussing before. This is rare events here. But you have a kind of dome here, below which the system will be a superfluid. So you see that here, repulsion between bosons are first a delocalizing effect. They make this kind of pot of bosons explode, and this delocalize the bosons. The system becomes a superfluid, and the superfluid is resistant to disorder. It passes over disorder as if it doesn't exist. But if you crank up too much the repulsion, even for an infinitesimal disorder, the system will turn back into a localized state, which is the Bose-Glass, where essentially bosons will localize. I represented it because I don't know how to represent it otherwise as individual particles, but again, I insist it's a many-body localized state. It's not something where you can say I localize boson 1, boson 2, boson 3. They interact. Yes? Okay, that's a very good question. I'll not say anything during this lecture, but there is the other lecture, and we'll come back to this. That's, of course, a very interesting question. The answer is not much, but I can put replica symmetry breaking on the top of the not much. At the time the name was coined out, it was mostly a name, just to say that this is not ordered, this is... so don't take the name glass too seriously. Yeah. It's not the Bose crystal. It's a Bose. Voilà. So, but Bose is difficult to print on the PhysRev B, so you have to put another name. Okay. This was, by the way, generalized to 2D and 3D by Matthew Fisher and collaborators in a beautiful paper. And you get essentially the same physics than the one we had found earlier with Einschulz in 1D. Just to... Yep. Yep.
The blue line is pathological, yet if you have a very small level of interaction, still you have something, it's continuous.
It's continuous, but if you look, for example, at the density, on this line, there is a finite region where the density is infinite and all the rest is zero. As soon as you will get finite interaction, there is an average density, which in average is everywhere finite. So there are still quantities which have a discontinuity across this line. But you're totally correct. Very close to this line, this really looks like puddles, which are very weakly connected, because then you find the next rare events very far, and you locate a lot of other bosons, then you find another rare events, and so on. But as soon as you have repulsion, you need to have a finite density on the system. If you have really no interaction, you find the best rare region, and you put everybody there. So this is still a little bit pathological. Okay, no other questions? So there are things that one can study for this transition, which to the best of my knowledge have not been observed experimentally. They have been observed numerically. For example, you can measure the Fourier transform of the momentum distribution for cold atom people, the G1 correlation function, and you find it decays as a power law in the superfluid at 0 temperature with an exponent that depends on the interaction. And at the transition, this exponent takes a universal value, which is 3/2. So this decay as 1/r to the power 1/3. So there is a universal behavior of the momentum distribution right at the transition between the superfluid and the Bose glass. In the Bose glass phase, the momentum the G1 correlation function decays exponentially because all states are localized, and so you essentially expect an exponential decay of this. The psi is the many-body equivalent of the localization length that you would get for single particles. Of course, its expression is not the same than the one you would get by solving the Schrödinger equation for one particle at energy E. You have a value, I'll show it to you later, which depends on the interaction, which depends on the strength of the disorder, and which is quite, it's a power law of the strength of the disorder. But you can define through this relation the equivalent of a localization length which describes the system. So this is a many-body localization length that we have in this system. So in a way, if you're on a lattice, you get 3 types of phases. You can put one boson in each one of the minima, and then you get something where if you try to add one additional boson, you would pay a finite energy. This is an incompressible phase. This is the so-called Mott insulator, 1 particle per site, if you want, per minimum of the potential. It has no superfluid order, but it's also incompressible. If you try to change a little bit the chemical potential, you cannot add particles. You have, of course, the superfluid, which I don't know how to draw, which is phase coherent. It's compressible, so if you try to add particles, you can easily do it. You just change a little bit the chemical potential, you add particles. And it has a sort of phase coherence in 2D and 3D. In 1D, it has power law decay of the correlation of this thing, so it has quasi-long range order in the phase, if you want. And you have the Bose glass, which is a kind of intermediate because it's compressible. You can find regions where you can add particles. You push a little bit the others. Again, it's a many-body state. It's not individual particles. But it's compressible. You can compute the compressibility. But, of course, it has no superfluidity. This correlation function decays exponentially. So that's, again, this is a many-body state. You cannot define the localization length of a given one particle. That has no sense. All the particles interact. Okay. There are many studies. I don't want to go too much into details. This was, of course, a very good problem for people doing numerics. So I've quoted here various reference, but you can continue. You will see even more recent reference later. Here is, for example, something coming from the group of Uli Scholvek in the last century. This was when they had computers which were turning still with a crank, and you know it was slow. And now, of course, they have quantum computers and it goes much faster. I'm sorry, I forget that I'm recorded here. Shouldn't say that. No, more seriously, so this was a very beautiful numerical study where they studied for the Bose-Hubbard model, so a model on a lattice, so there are sites. There is a repulsion U on when two bosons are on the same side of the lattice, and what is called delta here is the strength of the disorder. So you see that this is essentially the phases that I was discussing. You see the Bose glass that occurs at large delta, or the reentrance of delocalization by the interaction, then relocalization by the interaction. But of course, because you're on a lattice and because you have also one particle per site, if the repulsion U becomes too strong, you have also the third phase that I was mentioning, the Mott insulator, that appears on this phase diagram. They could have done the calculation with one boson every two sites, and in which case the Mott insulator would not have been there, but for practical reason at the time, they needed to do it with one boson per site. And you see essentially the nice, confirmation of what I showed you before, which was derived analytically by field theory, essentially. People have also studied other potentials, both because it's interesting and stimulated by experiments in cold atoms. So here is a Harper potential, which is made of two sinusoidal modulation, so it's not really disordered. There is no disorder, but these two components here are incommensurate between each other. So if you say one of the components is very deep, so if I say V0 is much larger than V1, you can sort of see the first component as defining a lattice. And then because the second component is incommensurate, you could say that this is like putting random potential on the top of the sides of the lattice. And so people were expecting that this type of system, I don't know where my cursor went, dead, strange. Ah yeah, it's back. But people were expecting that this type of potential would lead to very similar effects than the real disorder, the one which has really white noise. And actually, this is a model that has been extensively studied. It's known as the Aubry-André model. And this model is indeed known to have a localization transition. So contrarily to the real disorder, there is a threshold, and you need the second potential to be equal to twice the hopping on the site of the lattice to get the localization. So it's a little bit different, but in a way, this is close enough to the real disorder that it can be used to study this problem. And actually, for experimental system in cold atoms, this is very used because it's easy to produce by putting just two pairs of lasers on the system. This is quasi-periodics, and this is a very nice field of studying the competition of interaction with quasi-periodic potential. Here I put some ancient reference, not for the Aubry-André model, but we studied Fibonacci sequence, and that's produced some fun. So the Aubry-André model, you can study, it was studied by various people using, for example, numerics, density matrix, renormalization group calculations, and lo and behold, you find phase diagrams that look very much like the one for the true disorder that I showed you. This is the strength of the second potential, which here is called V2, here was called V1, because here it was numbered V1, V2 instead of V0, V1. And here is the strength of the local repulsion. And you see the phase, the superfluid phase, and you see the Bose glass, and you have here the Mott insulator, if you have exactly one particle per site, just like you would expect with a true disorder. Okay? Yep, sorry. Yeah. Exact. Absolutely correct. And you can show that this is a feature that you do expect for the true disorder. Here you get small differences between this and the true disorder. The other difference is that you notice that you get a finite threshold here at zero interaction to get the localization. So there are small differences between these two types of disorder, if I could say. One is a disorder, honest disorder. The other is a quasi-periodic potential. And the two phase diagrams are not identical, but I would say globally they show very similar features. So you're perfectly correct. Here you have this sort of sliver of superfluid which extend and separate the Bose glass from the Mott insulator, while you can show, and this can be shown by analytical also arguments, that on the contrary, for the other, it's the opposite. You should always have a sliver of Bose glass between the superfluid and the Mott insulator. If you draw the phase diagram in a slightly different way, where you would put the repulsion here, you would put the Mott phase here. What it means is that the Bose glass is always around, and this is chemical potential here. So this is for the true disorder, you have this property that you don't have for this one. This one is much more sensitive to the filling. Here is, for example, the same phase diagram that you would get, but at a different filling, not n equal 1 for the strong lattice, but n equals 0.5, which is incommensurate with either the strong lattice or the V1 lattice. You see that now the Mott phase has completely disappeared, and you get this superfluid phase at small V2 and the Bose glass phase at strong V2. So again, depending on what is your taste, you could say this is quasi-periodic. For me, it's a different problem. Or you could say, well, this is something I can realize, and I can study already a lot of properties, and I think it's a good attitude to look at what happens to this. Are there other questions on this one? Okay. Recently, we looked at with Epeng Yao, who was a PhD student of Laurent Sanchez Palencia in not in Institut d'Optique, sorry, in Palaiseau, in École Polytechnique, of what would happen if instead of looking at a very strong lattice plus a small perturbation, we look at two lattices which have same strength of potential. Why do we want to do this? It's because if you put here a very strong lattice, it's a killer in terms of temperature, in the sense that the kinetic energy becomes very small, and therefore the thermal effect will be very strong. And we wanted to try to give the Bose glass a better chance to be seen. I won't go into details, but essentially this is using quantum Monte Carlo calculation, and you see that so this is chemical potential here on the vertical axis, essentially. And the horizontal axis is the, of course, the interaction, is the scattering length. And essentially, you see that you have the three phases that one expects: the superfluid, the Mott insulator, the Bose glass. And it's a little bit more easy to access the Bose glass if the two lattices are of the same order. It was not obvious that there would be a Bose glass surviving, but it does. And so hopefully people will be able to do better observations with this type of potential, because again, the thermal effects, which are impossible to suppress completely, will be weaker if V0 is moderate than if V0 is gigantic. Okay, so this is the theory. People tried, of course, to observe this many-body localized phase, which is the Bose glass, again, or LEAP, localization of interacting particles. There were old experiments that I will not comment too much on Josephson junction arrays, on disordered superconducting films. You see here the resistance as a function of temperature of a 2D superconducting film, and you see a very clear difference. Here the resistance goes very large, here the resistance goes very small, so you could want to put here a superfluid or superconducting to insulator transition. This is something that was heavily studied in the early 90s. People studied helium in porous media, and so there were remarkable experiments. But I would say the thing that made really a new playground for this kind of physics were cold atoms. Here is an image where you see 1D tubes with two lasers which create the double periodic potential that I was mentioning, which is coming from lens. I will show you more details on this experiment. People have now also realized beautiful superconducting films which are trapped between two insulating materials, the so-called LAO-STO interface, which allow to realize really very nice 2D superconductors. And I won't have time to discuss on this aspect, but this is really a pity because I think it's a very promising direction, which is to use spin systems. Because, you know, spin 1/2 is a boson. It's a hardcore boson. Spin down, absence of boson. Spin up, presence of a boson. Hardcore means you cannot put two bosons on the same site because the spin 1/2 has only two states. And you can use magnetic systems to hunt for the Bose glass, and there has been beautiful experiments that were done in this direction. So I've just put a couple of references here, and I'll be very happy to discuss more on this. Here is one example of a paper that was published 10 years ago now in Nature, where people study the phase diagram of one of these compounds, which is called DTN, and find a Bose glass phase in this material that can be analyzed by various techniques. Let me skip that. Let me show you the results in cold atoms. This is an experiment which were done in the group of Giovanni Modugno and Massimo Inguscio in Florence. And we helped on the theory, and the main players there were Guillaume Roux and Thomas Bartel for analyzing the experiments. So the setup were 1D tubes with this Harper potential, this quasi-periodic potential. And here is the phase diagram that was obtained. What is plotted here is the width of the momentum distribution. So if you have a superfluid, you can expect this width to be very narrow. If you have a localized phase, this is the Fourier transform of an exponential, so this is a broad Lorentzian. One can do this more quantitatively, but essentially you see the phase diagram where you have here the superfluid phase, and here you have a phase which is clearly with a much broader width, and other probes like shaking the lattice and so on confirm that this is a localized phase, and at least for this part that this is something that we want to identify as a Bose glass. So there is experimental confirmation that at least this phase diagram is not completely crazy. Now, unfortunately, in this system, the thermal effects are pretty high. Here is the theoretical widths that we should have had for the momentum distribution, and the red line and the line that you see below. The red line is the theoretical line taking into account the thermal broadening and the broadening due to the inhomogeneities in the tubes, because of course the system is in the trap, so the chemical potential varies from tube to tube, and I'm sorry to insist, but I think in cold atoms, people should get rid of the trap. Okay. I said it. I cannot not say it. And you see that the theory and the experiment fit very, very well. But nevertheless, this needs a strong sort of reconstruction of the experimental results. And it would be much better to see them directly on the experimental curve. So this is for the thermodynamics, and in the 10 or so minutes that I've left, I would like to discuss the transport, because after all, if we discuss localized versus non-localized or whatever, again, one of the important quantity is not the phase diagram, but it's the transport properties. So if we have no interactions, in 1D, there is a beautiful solution that was provided by Berezynski, the same Berezynski than the BKT transition, the Berezynski-Kostelis-Thouless transition. He solved completely, essentially, 1D non-interacting, let's say fermionic, but it doesn't matter, systems. And here is what his solution will give for the conductivity. So here is the frequency-dependent conductivity as a function of the frequency here. And this is 0 temperature. And as I said, if you put the temperature on the non-interacting system, you don't change anything, essentially. But here I'm at 0 temperature. And you see a very characteristic curve, which has a maximum here, and two behaviors, a behavior above the maximum and a behavior below the maximum. Why the maximum? Because you get sort of pinned region of size, the localization length, and if you put an oscillating field, it's like shaking something in a bowl, and you know that if you had only one sort of restoring force, if you have an harmonic oscillator and you shake it, when you're in resonance with the frequency of the bowl, you get a peak. Except here, instead of one peak, you get something broader because there is a whole distribution. But you can expect this maximum to be around the inverse of the localization length. And indeed, lo and behold, this is what Berezynski's solution will give you, that this maximum here is a way to extract the localization length of the problem at the Fermi level for fermions. Okay. Now, if you excite too fast, then you cannot make your system really move, and you lose the signal here as 1 over omega square. And what is interesting is if you excite at very small frequency, you find that you get an absorption which is omega square, essentially. And the guy who understood the omega square is again Sir Neville Mott, again without any calculation. So I love this calculation. He said, okay, what is the energy absorbed? The energy absorbed is sigma, the conductivity, times E square, the electric field square. That's V times I. Now, what is the energy absorbed in a quantum problem? It's h bar omega every time I'll do a transition, times the number of transition, and the number of transition is the density of state times h bar omega. So this is proportional to omega square. Sigma is proportional to omega square if I have localized state, assuming that the density of state doesn't vary too much between the localized system and the bare system. So again, there is a kind of physics with the hands, but you see it works. Now you could say there is a log square, so maybe Mott didn't catch the log square. The guy who caught the log square is Bert Halperin, which is also a very smart person. And essentially, the log is a little bit more complicated to explain, so I won't do it here, but it has to do with the overlap of the localized wave function. You need to be able to do the transition, and it's relatively easy to show once you know that you have a log square in this formula. So you see this very beautiful frequency-dependent conductivity that people compute completely for the non-interacting system. And one of the questions is, how is this modified when you put interaction in the system? So the first thing is that the localization length is modified, and this is what I told you before. Now the localization length is not 1 over the disorder anymore, as it was for non-interacting system in 1D, but it's modified by the interaction by an exponent which is dependent on the interaction. So you get a sort of many-body localization length here, which is dependent on the interactions. So you expect the same potato for the sigma of omega And above the localization length, the 1 over omega square is very much affected by the interactions again, and is changed to a new power, which again depends on the interaction, which can be computed, and which shows the combined effect of disorder and interaction. If you go to low frequencies, that's not so easy to compute because you cannot use the RG. So there are various techniques that one can use, which I will talk in the other lecture. But what you could naively expect or anticipate is that you should still have an omega square, because in a way, once you localize the particles, well, they will not see each other very much. So their interaction effect should be very much reduced. So you could expect seeing things reasonably close to the non-interacting system. So this part can be obtained out of the RG technique that I mentioned before. And so let me show you a very recent result that we obtained with Shintaro Takayoshi, with faculty in Japan. And this is trying to study numerically, by using a modification of the DMRG technique, this transport in 1D in regimes where the analytics have problems going. So essentially, this part here is extremely difficult to extract analytically. So we looked at bosons on a lattice, hardcore bosons with the nearest neighbor repulsion, random potential. So this is a spin chain for the professional. This is an XXZ spin chain plus a random magnetic field on site. So if we set delta equals 0, this is no interaction. We have Berezinski solution. And lo and behold, we find back exactly what we should find. The peak here scales perfectly as a function of the strength of disorder, as it should. Of course, no doubt that Berezinski's solution was correct, but it's just for us to know that we are also correct. And the value of the conductivity at the maximum scales perfectly. And now when you put interaction, here is what we get. You see the curves are a little bit more complicated. So this is, for example, for various strengths of the disorder, W, for a fixed value of the delta, which is fixed to 1/2, if I remember correctly. And you see that when you change the strength of disorder, well, the peak moves because the localization length moves. And when you do the scaling of the position of the peak and the value of the peak, you find something which is in very good agreement with the theoretical formula that I showed you, that you get a power law with an exponent which is a function of the interaction. We know what is this parameter k as a function of the interaction, so we can check that indeed our many-body result is correct. The thing which is working much less satisfactorily, and at that stage I don't know really why, is the fact that the field theory would also give you normally the decay at a large frequency of the tail of the conductivity. And again, we know in principle this exponent out of the field theory. This is the dashed curve here. And you see that the numerical results show decent agreement when the interaction is repulsive, but for some reason we have strong deviations when the interaction is attractive between the particles, and there is no a priori reason why. So this is a mystery. We don't know really what is going on between the numerics and the analytics. The part where we would really be interested in getting results is, of course, more the other side, which is the small frequency behavior. All this is t equals 0. And you see that now if you start changing the interaction, you get dispersion in the curves. But when you rescale the position of the maximum, you get curves which are still reasonably compatible with a law which is omega square log square. So it seems that indeed this law is robust at small frequencies, even in the presence of interactions. Of course, the $1 million question now would be to put a finite temperature and then see where this curve go at finite temperature, whether they go to a finite value, in which case we have a finite conductivity at finite temperature. This is interacting systems here. Or whether they stay to 0 at finite temperature, in which case we have at least a threshold of zero conductivity even at finite temperature, which is certainly one of the points which are discussed by many-body localization. So here we are discussing about a system which is an isolated system where we analyze the conductivity using Kubo formula, and there are issues that we would like to address here concerning the thermal effects. For the moment, this is beyond the power of what we can do numerically, but okay. Let's see whether either some analytical calculation or improving a little bit on the numerics could give us the answer. If you look at DC transport, the static transport, here again, the RG calculation gives you the high temperature result, which is a power law, which is dependent on the interaction, a little bit the equivalent of the frequency dependence here. And there is no confirmation, but we could check, and I won't go into the detail of the calculation because my time is nearly up, that if you want to go in presence of a thermostat at low temperature and compute the conductivity, then you get the equivalent of Mott, let me skip all that. You get the equivalent of Mott variable range hopping, where you get objects that are able to jump from one site to the next site. And of course, it's not individual particles because there exist no individual particles. But in the field theory, these are solitons of a certain field, which is representing the density of particles. So we could identify for our many-body system a mechanism which is very similar to the mechanism of Mott variable range hopping. And we find an expression for the conductivity, which is also square root of beta, but where the coefficients here are not connected to the single particle density of state and whatever, but to these parameters which depend on the interaction, which are controlling the physics of the many-body problem. How to extend or use this calculation in the absence of a thermostat? For the moment, we have no idea how to do it. We really need the thermostat to do this calculation. But this is also another $1 million question. So if you want to compare with Sir Neville Mott, you add the beta, the square root of beta in 1D, d equal 1. But these coefficients are single particle coefficients, while here we get something which is the many-body thing. I just want to point out that we could see that these systems are showing some characteristic of glasses. They are showing aging. So this is a very exciting or tempting to make connections. So again, these are the field theories that one is using to describe this system. If you do a brutal change of the chemical potential, you will find that the density is showing an extremely slow dynamics. It's really moving with a lot of, let's say, slow behavior, which is akin to the one of glasses. And this will probably resonate with some of the things that Emmanuel will tell about doing density imbalances. Here it's not a density imbalance, it's just brutally changing the chemical potential. And of course, it's very tempting to try to connect. It's not obvious that there is a connection, direct connection, but to connect these aging properties with physics that people have advocated for many-body localization. So I'll stop here. I just want to give you a take-home message from this whole lecture. The first one is that there is a remarkable interplay between localization and interaction. It's a very difficult problem, but it's also a very exciting problem. And in a way, we have, I would say, certainly we don't have good tools, but we have better tools than we could have hoped to have given the complexity of the problem, especially in 1D. We made a lot of progress in 1D, both because of the progress in analytics in 1D, understanding field theory, and also progress in numerics in 1D. This has very deep consequences, but also present very strong challenge both for the equilibrium, the localization of interacting particles that I told you during these talks, this talk, and of course out of equilibrium, the many-body localization, as you will hear in the talks of Dima and Denis, and also on the experimental side, I guess, with in particular Emmanuel. And more importantly, both in equilibrium and out of equilibrium, there are beautiful new experimental possibilities to explore these phenomena, and this is really what we need to make progress on these difficult topics. We need, at some point, the experimentalists to bump us in the head and tell, you know, look, what you say is bullshit. You need to go back and recompute. And on the theory side, even without worrying about the aspect of ergodicity and out of equilibrium, we clearly need better tools to be able to deal with a finite temperature than we are able at the moment. We have, I'll discuss more tools in the other lecture, but we have pretty decent tool to deal with the zero temperature properties. We are very defenseless as soon as we need to put a finite temperature. And on that, I will stop, and I thank you for your attention.